Good morning, students. In today's class, you will see the topic named reflector antennas. Parabolic reflectors are based on the geometric optical principles. Their feeds are also not by using a coaxial cable, but it uses the optical methods. We know what is a parabola. A parabola is defined as the locus of the points which move in such a way that its distance from a fixed point called as focus plus its distance from a straight line called as the directrix is a constant. The equation of the parabolic curve is already known, which is given by y square is equal to 4fx. A parabola with the focus f and vertex O is shown in the diagram. You can see the diagrammatic representation of the geometry of a parabolic reflector, which is a two-dimensional plane curve. You can see that you have the focus represented by f and the vertex represented by O. At the focus, you will be having the radiator which radiates or illuminates the reflector, parabolic reflector. So the wave incident is reflected by the reflector. So you have the incident angle represented by I and the reflected angle represented by the parameter R. The dimension of the aperture is represented by D. So we have OF, which is the focal length, or it is simply represented as F. K, which is a constant, depends on the shape of the parabola. F is the focus, O is the vertex, and O dash is the axis of the parabola. So the open end of the parabola, we call that as the aperture. One of the important characteristics of any reflector antenna is the F by D ratio, which is called as F over D ratio, which usually varies between 0.25 to 0.5. So the beam formation or the focusing of the reflector antenna is mainly understood by keeping a source at the focus of the parabolic reflector. So if you have any source which is kept at the point F, the rays which are originating from the focus will be reflected by the parabola, and the reflected waves reaches the aperture as a parallel plane. So since all the waves are in phase with each other, a very strong concentrated beam of radiation will be available along the axis of the parabola. So next is paraboloid reflector antennas, which is called as microwave dish. So parabola is a two-dimensional plane cave. A practical reflector is a three-dimensional curved surface, which we call as paraboloid reflectors, or called commonly as microwave antennas or microwave dish antennas. So how this is formed? This is formed by rotating the parabola about its axis O dash. So the surface generated by this method we call as paraboloid, which is often called as a microwave dish or a parabolic reflector, as shown in the diagram. The paraboloid produces a parallel beam of circular cross section, because the opening of a paraboloid will be circular in nature, so it produces a circular cross section of parallel beam. And we know the equation of the paraboloid, which is y square plus z square is equal to 4fx. So we have z square, which is added to the normal parabola, where z is the third Cartesian coordinate, which will be perpendicular to both the axes x and y. And the second diagram gives the radiation pattern of a paraboloid with an aperture d is equal to 10 times the wavelength, that is 10 lambda. So we have a stronger beam. So it is a unidirectional antenna where we have a stronger beam along the axis of the parabola. If we feed, or the primary antenna is going to be an isotropic, which radiates energy uniformly in all directions. In such a case, paraboloid will be producing a strong beam of radiation. Assuming that the aperture is going to be a circular aperture, the beam width between the first null is given by the formula BWFN is equal to 140 lambda by d degrees, where lambda is the free space wavelength in meters D is the diameter of the aperture in meters, that is the mouth diameter, opening diameter. The beam width between the fastenals for a large uniformly illuminated rectangular aperture. If the aperture is going to be rectangular instead of a circular, then BWFN is given by 115 lambda by L degrees, where L is the length of the aperture in terms of wavelength lambda. The width between the half power points of a large circular aperture is given by half power beam width HP BW is equal to 58 lambda by D degrees. The directivity of a long uniformly illuminated aperture is given by D is equal to 4 pi A by lambda square. If the aperture is going to be circular, then its directivity is given by D is equal to 9.87 D by lambda the whole square, where D is the diameter of the aperture in lambda. In practical cases, the feed, that is the primary antenna, will not be isotropic in nature. So we will be having some noise or radiations. So the radiation will not be uniform because of the non-isotropic nature of the practical feed antennas. So that results in less capture area. So actual area will be larger actually, and the capture area will be lesser. So which is given by A0 is equal to K into A, where A0 is the capture area and A is the actual area of the mouth or the opening of the parabolic antenna. K is a constant which depends on the type of antenna used for feeding. So normally if a dipole antenna is used as a feeding antenna, then K value is approximately 0.65. The power gain of a circular aperture paraboloid with respect to a half wave dipole as a feed is given by GP is equal to 4 pi A0 by lambda square. Substituting the expression for A0 as K into A and substituting A of a circular aperture as pi D square by 4, we get the expression for the power gain of a circular aperture paraboloid as 6.389 D by lambda the whole square. So approximately we can write the circular aperture, for a circular aperture the power gain can be approximately written as GP is equal to 6D by lambda the whole square. So a paraboloid reflector can be designed by keeping the mouth diameter fixed, that is by keeping D as fixed. By varying the focal length F, we can design the parabolic reflector. So three cases are possible under this. First case is the smaller focal length. So the focal length is going to be smaller. You can refer the diagram A, where F is less than D by 4. So in that condition what happens, the focus lies well inside the mouth of the focus of the parabolic reflector will lie inside the mouth of the aperture. So it becomes difficult to get a source giving adequately uniform illumination over such a wide angle. So second case is larger focal length. We can refer the third figure, that is figure C, where F is greater than D by 4. In that case what happens, the focus will lie beyond the opening of the mouth. So if you consider this as the opening of the mouth, then F is going to be beyond that. So it becomes difficult to focus all the radiation from the source on the reflector. Third case is the focal length which is equal to 1/4 of the open mouth diameter, that is F is equal to D by 4. So you can refer the diagram B where F is equal to D by 4. So this figure B, this construction will give a maximum gain. So the radiation beam of a paraboloid reflector antenna is theoretically pencil shaped. So very narrow beam will be available along the axis of the paraboloid reflector antenna. The types of parabolic reflector antenna. So in previous case we have seen a full paraboloid reflector. Other than this category, we also have three more categories which will utilize the properties of the parabolic reflector. There are three dominant reflectors available, namely the cut paraboloid reflector or truncated, where upper half or the lower half of the full parabolic will be cut to form such a truncated paraboloid. Then we have the second case as paraboloid cylinder reflector with line source of 8 dipoles. So 8 dipoles are kept to feed a parabolic cylinder reflector. The third case is pillbox, or also called as cheese antenna, as shown in the diagrammatic representation. So next topic is the feed systems of parabolic reflector antennas. So feeding the reflector antenna is very important concept. So parabolic reflector antenna consists of two basic components. Number one, the reflector. Number two, the primary source which is kept at the focus, which provides the required radiation. So the source is called the primary radiation, or it is called as feed radiator, or simply it is called as feed. And the reflector, the paraboloid, it is called as the secondary radiator. Dipoles also can be used as feed antenna, but it provides lesser efficiency. So Yagi-Uda will be used, and most commonly used feed antenna is waveguide horn. So you can see the diagrammatic representation. The first case where the dipole, that is Yagi-Uda antenna, is used as input, used as a feeding antenna, or the primary antenna which feeds the paraboloid. In the second case, it is the waveguide horn antenna. In the third case, it is waveguide supported by a small paraboloid. So Cassegrain feed is another important feed method for parabolic reflector that is available. So in this Cassegrain feed, a primary feed radiator is positioned around the opening near the vertex of the paraboloid instead of its focus. So this is very important point to be noted. So Cassegrain feed system employs a hyperboloid secondary reflector. So you have main reflector and as well as a secondary reflector, whose one of the foci coincides with the focus of the paraboloid. The feed radiator is aimed at the secondary hyperboloid reflector or the sub-reflector. In the diagram you can see you have the focus. So this F focus is the focus of paraboloid, as well as this hyperboloid, which is the secondary reflector. Paraboloid is the main reflector. The main reflector is provided with the horn waveguide feed. Using a feed horn feed, we are radiating the sub-reflector, that is the hyperboloid. This hyperboloid will reflect the signal to the main reflector, and that gets reflected, and we get the plane of parallel waves. So this is the concept of Cassegrain feed, where we use a main reflector as well as a sub-reflector. The radiations emitted from the feed radiator are reflected by the Cassegrain secondary reflector, which illuminates the main paraboloid reflector as if it's originated from the focus. So when we look at it, it looks like the radiation is obtained from some source available from the focus, as in the previous cases. So actually there is nothing at the focus. We are having a hyperboloid, a secondary reflector inside the focus or at the vertex of the paraboloid, and we construct this Cassegrain feed with the help of a horn antenna. So next we will move on to the advantages and disadvantages of Cassegrain feed. The main disadvantage of Cassegrain feed is, you can look at the second diagram. So since you have the reflector, since you have the hyperboloid sub-reflector at the vertex, some of the rays are blocked at the center. So the main disadvantage is, some of the radiations from the paraboloid reflector is obstructed by this hyperboloid sub-reflector. So this is tolerable when the size of the antenna is going to be very large, but when the dimension is very small, this becomes a larger problem. So the dimension of the secondary reflector depends on the distance between the horn feed and the sub-reflector mouth of the horn, which in turn depends on the frequency. So this aperture blocking defect can be avoided by using an offset reflector. That is, instead of keeping the hyperbolic reflector at the center, we can go for the second diagram where it is kept at an offset, where the center radiations are not blocked. So advantages of Cassegrain feed are reduction in the spillover and minor radiation, ability to get an equivalent focal length much greater than the physical length, ability to place the feed in a convenient location, capability of scanning or broadening of beam by one of the reflecting surfaces. So these are all main advantages of Cassegrain Feed. Thank you.